There is a mountain in the Chilean Andes where the air is so dry and so thin that the stars don't twinkle, they burn. Cold and still and absolutely precise, like holes cut through black fabric, each one fixed in its place, as if the sky itself were holding its breath. On the summit of this mountain, a machine waits for darkness. The moment the sun drops below the horizon, a dome the size of a small building begins to rotate. A mirror 8 meters across, larger than most apartment rooms, tilts toward the sky. And then the machine begins to do something no telescope in history has ever done before. Every 40 seconds, it captures an image larger than 45 full moons. Then it moves, captures again, moves again, all night, every night, for 10 years. Within a few nights, it will have covered almost everything the sky above this mountain allows it to see, and then it will begin again from the start. By the time this decade-long survey is complete, it will have stared at every point in that sky roughly 800 times, building a time-lapse movie of the universe so detailed, so vast, so relentlessly complete, that astronomers are already using a word they rarely apply to telescopes: unprecedented. But here is the thing that nobody is saying loudly enough. In the very first weeks of operation, before the real survey had even properly begun, this machine started finding things that were simply not on our maps. Objects in our own solar system that humanity had never seen before, and hints of something in the deep outer solar system whose existence, if confirmed, will force us to redraw every chart we have. This is the Vera Rubin Observatory, and what it is already seeing is just the beginning. To understand why the space science community has been waiting for Vera Rubin with something close to held breath, you need to feel the scale of what it is doing. Not just understand it intellectually, but feel it. Every great observatory before this one worked like a spotlight. You point it somewhere specific. A star, a galaxy, a patch of sky that interests you, and you stare, for hours, sometimes for days, drinking in the faint light from that single chosen target. This is how Hubble operates. This is how the James Webb Space Telescope operates. They go deep and narrow, peeling back the layers of a single scene with extraordinary precision. Vera Rubin operates on a completely different principle. Its field of view is so wide that a single image swallows an area of sky that would take 2,000 separate Hubble photographs to cover. And rather than choosing a target and waiting, it moves continuously, covering the entire accessible sky in just a few nights, then starting again from the beginning. The camera that makes this possible took 20 years to build. The LSST camera is the largest astronomical digital camera ever constructed. 3,200 megapixels, roughly the size of a small car, cooled to temperatures colder than the surface of Pluto to keep its detectors quiet enough to register the faintest possible signals. A single one of its images, printed at full resolution, would require a billboard the size of a sports stadium, and every 40 seconds, the telescope produces another one. The data flowing out of this machine every night amounts to roughly 20 terabytes. Over its 10-year legacy survey of space and time, Vera Rubin is expected to catalog approximately 20 billion galaxies and 17 billion individual stars with measured properties. Millions of asteroids, hundreds of thousands of exploding stars. And somewhere in that torrent of data, almost certainly, things that have never been seen before and don't yet have names. The telescope began issuing live scientific alerts in February 2026. On its first full night of alerts, it generated 800,000 individual notifications, each one representing something in the sky that had changed since the last time the machine looked at that spot. A new light, a brightening, a movement. At full survey tempo, that number is expected to reach 7 million alerts per single night. 7 million changes in the sky, detected and reported every 24 hours. The universe, it turns out, is not the static cathedral of light we thought we were looking at. In about 10 hours of data collected across 7 early commissioning nights, the Vera Rubin Observatory discovered 2,104 asteroids that humanity had never seen before. Among them were 7 near-Earth objects, rocks whose orbits carry them into the neighborhood of our planet. None of them are currently threatening, but pause on that number for a moment. 7 previously unknown near-Earth asteroids found in the very first days of operation, before the full survey had even started. Astronomers estimate that over its first 2 years of full operation, Vera Rubin will discover more asteroids than all previous telescopes in history combined. What this reveals is not that the solar system is suddenly more dangerous than we thought. What it reveals is that our previous picture of the solar system was profoundly incomplete. We were navigating with a map that had enormous blank regions, and we didn't fully appreciate how large those blank regions were. The planetary defense implications are direct and serious. For decades, the most urgent priority in asteroid tracking has been the kilometer-scale objects, the civilization-ending threats. That catalog is now reasonably complete, but the middle range, objects between 100 and 500 meters, large enough to devastate a continent or trigger a global climate disruption, remains poorly mapped. That is the gap Vera Rubin will systematically close, one night at a time, building a census of the near-Earth population that is comprehensive in a way nothing before it has been. And beyond asteroids, the observatory is watching for something rarer and stranger: interstellar visitors. When an object designated 3I/Atlas entered the solar system in 2025, it joined only 2 confirmed interstellar objects ever detected: Oumuamua in 2017 and Borisov in 2019. These are pieces of other solar systems, flying through ours on hyperbolic trajectories, carrying chemical and structural information from environments we will never physically visit. Each one is a message in a bottle from somewhere unimaginably far away. Vera Rubin's continuous sky coverage means that the next interstellar visitor will be detected earlier, at greater distance, with more time for follow-up observations before it reaches its closest approach and accelerates away forever. Over a 10-year survey, the number of confirmed interstellar objects is expected to increase dramatically, and each new one is a piece of data about the composition and dynamics of planetary systems across the galaxy. What we don't know, and what makes this genuinely compelling for those paying close attention, is what an unbiased, comprehensive survey of the outer solar system might reveal that all previous targeted searches never found. The earlier inventories were limited by where and how astronomers chose to look. Vera Rubin has no such constraint. It looks everywhere, every night. And the outer solar system, as we are already beginning to see, is not empty. Here is a fact that should stop you for a moment. Everything you have ever seen, every star, every galaxy, every nebula in every photograph, every atom in your body, every planet orbiting every sun, accounts for approximately 5% of the total content of the universe. The remaining 95% is invisible. Dark matter, which makes up roughly 27% of everything, does not emit light, does not reflect light, and does not interact with light in any way that our instruments can currently detect. We know it exists only because of what it does to the things around it. The way it bends the path of light passing nearby. The way galaxies rotate far faster at their edges than the gravity of their visible stars alone could possibly explain. Dark energy is stranger still. It constitutes 68% of the universe, and it appears to be the force driving the accelerating expansion of space itself. It doesn't cluster. It doesn't have a location. It is distributed through all of space, everywhere simultaneously, pushing everything apart at an ever-increasing rate, and we have essentially no idea what it is. The Vera Rubin Observatory was designed at its deepest level to confront these two mysteries directly. The method it uses is called weak gravitational lensing. When light from a distant galaxy travels toward us, it passes through the invisible dark matter surrounding nearer galaxies and galaxy clusters along the way. This dark matter slightly bends the light's path, not enough to form dramatic visible distortions, but enough to introduce tiny measurable changes in the apparent shapes of the background galaxies we observe. By measuring those changes across billions of galaxies, astronomers can map the invisible dark matter distribution, not at a single point in time, but as it has evolved across billions of years of cosmic history. Over its 10-year mission, Vera Rubin will catalog the shapes of 5 billion galaxies and apply this technique at a scale that was simply impossible before. The resulting dark matter map will be the most detailed ever constructed, and it will either confirm the current cosmological models with extraordinary precision, or reveal systematic discrepancies that demand something fundamentally new. That second possibility is more likely than it might sound. There is already a deep tension in cosmology that current models cannot fully resolve. When astronomers measure the expansion rate of the universe using the ancient microwave background radiation left over from the Big Bang, they get one number. When they measure it using nearby supernovae as distance markers, they get a different number. The gap between these two measurements has persisted for years despite intensive efforts to find the error, and it is now statistically significant enough that most researchers believe it is real, meaning that something in our current understanding of the universe is incomplete. Vera Rubin will produce independent measurements of cosmic expansion using its lensing data, and those measurements will sharpen this picture considerably. Either the tension resolves and the models hold together, or it deepens, and something genuinely new enters physics. Both outcomes matter. Both outcomes change something. In the outermost reaches of the solar system, beyond Neptune, beyond the Kuiper Belt, there is a region of space that our instruments have never fully mapped. Objects out there move so slowly, are so faint, and are spread across such enormous volumes of sky that finding them has always required extraordinary patience and very deliberate, targeted searching. Over the past decade, astronomers studying this distant population of icy bodies noticed something unexpected. The orbits of the most remote known objects are not randomly distributed. They cluster. Their orientations align in patterns that gravitational simulations suggest cannot arise purely by chance. The most widely accepted explanation is the gravitational influence of a large, undetected planet, a world perhaps 5 to 10 times the mass of Earth, orbiting at distances so extreme that it takes thousands of years to complete a single revolution around the Sun. This hypothetical world has been called Planet 9. Its existence has been debated seriously since the hypothesis was first published in 2016. With researchers divided between those who find the orbital clustering genuinely compelling and those who believe it reflects the biases of how and where previous surveys were conducted, rather than a real object. Vera Rubin may not find Planet 9 immediately, but it will do something almost as important. It will test the evidence behind the hypothesis with the least biased, most comprehensive sky survey ever made, separating real orbital clustering from observational artifact for the first time, with data that covers the entire accessible sky. It will detect trans-Neptunian objects in numbers large enough to finally resolve the statistical question. And if Planet 9 itself exists at a distance where its reflected sunlight reaches detectable levels, the observatory's sensitive camera may find it directly. This is not only a question about one hidden planet, it is a question about the gravitational architecture of the outer solar system, the deep, slow structure that has shaped the movement of icy bodies at the edge of the Sun's influence for 4 billion years. What Vera Rubin finds, or does not find, in that region will tell us something fundamental about the solar system we actually live in, as opposed to the one we assumed we understood. Every major expansion of astronomical survey capability in history has produced surprises. Not incremental refinements of what was already expected, but genuinely unexpected discoveries. Things that were not in the models, not in the predictions, and not in the imagination of the researchers who built the instruments. The discovery of the accelerating expansion of the universe, the observation that gave rise to the entire concept of dark energy, came from a survey of supernovae that astronomers had expected would confirm a decelerating universe. The discovery of the first fast radio bursts came from archival survey data that nobody had looked at carefully before. The discovery of Oumuamua came from a survey telescope whose operators were not specifically searching for interstellar objects. In every case, the universe offered something that the prevailing model had not prepared anyone to find. Vera Rubin is conducting a survey 100 times more comprehensive than anything before it, generating 100 times more data per night, with automated alert systems specifically designed to flag anything that does not match the expected behavior of known object classes. The probability that this machine, over 10 years of continuous, unblinking operation, will encounter something that falls entirely outside existing categories is not small. It is, by any honest statistical reasoning, quite high. What that discovery might be is impossible to predict. That is precisely the nature of it. It could be a new class of astrophysical event. It could be an object moving through the solar system in a way the known gravitational architecture cannot explain. It could be a pattern in the dark matter distribution that forces a fundamental revision of cosmological theory. It could be something more subtle, an anomaly so persistent, so well characterized in the data, that it points toward physics that currently exists only as speculation. The Vera Rubin Observatory will not answer all of the questions we already have. What it will do is provide the richest, most complete observational record in the history of astronomy. And in that record, the answers to some of the deepest questions we carry, alongside questions we don't yet know enough to ask, are almost certainly waiting. A machine on a mountaintop in Chile opens its eye every 40 seconds. The sky it is watching is stranger, more populated, and more alive than any map we have drawn of it.